Well, good morning, chemistry team. We are coming at you again with more intermolecular forces. This is our last one, though, so we've covered quite a few. So I branched one video into ionic forces. So we had ions, cations with anions. To me, that's the easiest, positive, negative, pretty simple. And then ion dipole, ion with a polar molecule, and then ion induced dipole, an ion with a nonpolar species. Pretty straightforward. And then we looked at dipole forces, so dipole, polar molecule with a polar molecule. We looked at dipole-induced dipole, so a polar molecule with a nonpolar species. So we're cranking through. And then we looked at hydrogen bonds as a specific case of dipole-dipole forces with the pretty extreme restrictions on there. So know those restrictions. But hydrogen bonding is probably the one you learn more about when you take most of the other sciences outside of chemistry, because it has so much, biochemical applicability. It's pretty cool. Hydrogen bonds are pretty cool. But we're going to look at London dispersion forces today. This is the last one. Typically, they're thought of as a nonpolar molecule with a nonpolar molecule, but that's not technically correct, all right? These were the hardest ones for me to understand as a student. I can understand positive and negative ions, even polar molecules, right, with the partial positives and partial negatives. I can grasp those, the electrostatic stuff. But London dispersion forces were a little trickier for me to grasp my brain around because it didn't make sense how they even started in the first place. But we'll talk about what they are. But we got to remember those terms: polarizability, right? The tendency for a species to have its electron cloud distorted by another species, right? So even nonpolar species, right? If they have an electron cloud, you bring some positive or negative region around it, those electrons are going to shift around. That electron cloud can go from symmetric to asymmetric, right? So, and the larger it is, the more polarizable it is, the more susceptible to having its electron cloud distorted. And then the other term, induction, right? Which we talked about, right? Having that electron cloud, the process of having your electron cloud distorted by something else is induction. That's why you get that induced dipole term, ion-induced dipole, dipole-induced dipole. The permanent polar molecule or the ion is inducing a dipole on a nonpolar species, right? But any species with electrons can have those electron clouds shifted around a little bit and distorted, right? So this particular intermolecular force applies to everything that has electrons, right? We're talking polar molecules, nonpolar molecules, atoms, ions, polyatomic ions. Everything that has electrons has these. But we're going to look at the comparison of, well, how important are London dispersion forces for something that has other intermolecular forces as well? So if we've got a polar molecule, okay, are these forces going to have any extra impact above and beyond, say, a hydrogen bond or a dipole-dipole force? It gets complicated. All right. Technically, this is a shortcut name. London dispersion forces. I need the other half of my parentheses. Boop. LDF. So you'll hear these called dispersion forces. You'll hear them called London forces. Though that's the shortcut, cutesy name by, Fritz London, 1920s, I think, theoretically explained this. 1928? Don't quote me on that one. A while ago. Technically, these are called instantaneous dipole, induced dipole forces. That's a lot to eat for breakfast, okay? So let's go through and talk about what this means. You should be okay with the induced dipole, right? Something causing a distortion of an electron cloud on something else. That's induction, right? But what is this instantaneous dipole deal? All right, so let's look at that on the next board. Understanding everything that has electrons has this. The more electrons there are, the stronger the impact of this. So size really makes a big difference here. So let's draw some fictitious species and look at what this instantaneous dipole is. Whew, ready? All right, you ready? This took my brain a little thinking when I was a first semester general chemistry student, a second semester general chemistry student, actually. Briefly touched on in intro chem. You might have learned this in introductory chemistry as well. It's kind of important. So this might be a review for a lot of you. That's pretty cool. So we're looking at electron probability distributions, right? Quantum mechanics, all that fun stuff. So let's take a nonpolar species, could be an atom, could be a molecule. It's got a symmetric electron charge distribution. All right, perfectly the same everywhere. This could work for any species. Let's just focus on a nonpolar species. So, but the electrons aren't static, are they? They're moving around. So there is a small percent chance that at any particular, nanosecond in time, that's not going to be perfectly symmetric. The electrons are moving around. So you can get these flashes of electron density where there might be, probabilistically, is that a word? It is now, a few more electrons on one side than the other. So imagine it as, here you've got this electron cloud, perfectly symmetric of a nonpolar species, and then there's this flash of electrons on one side. The more electrons there are, the larger this effect. That makes sense, right? If you've got 10 electrons, right, versus 100 electrons, this is going to be more dramatic with an 100 electron effect. So the larger it is, the more impact this is going to have. But there could be this brief flash. Think of it as like a flash of electrons where you got a few more electrons on this side than this side, and then it just goes back again, right? So by itself, this really isn't a big deal, right? And so what happens is you get this electron flash. So temporarily, you get this electron fluctuation where you got a few more electrons, whatever, on this side than this side. So very briefly, you get this flash of this dipole. We call that an instantaneous dipole that briefly forms. So you got a little, really tiny partial negative on one side where there's more electrons and a partial positive on the other side where there's fewer electrons. And then it just goes back, right? So really, you can think of this as a reversible arrow where it's just flashing back and forth, mostly here, but every once in a while it'll flash and have this instantaneous dipole due to a temporary asymmetric electron distribution from the probabilities. By itself, no big deal, all right? But what if this flashes all of a sudden and you get this instantaneous dipole that's just briefly there for just a flash of time. But during that flash of time, this appears, there's another species near it, right? Could be the same species. If this is an argon atom, it might be another argon atom. If it's a methane molecule, it could be another methane molecule. If it's water, it could be another water molecule. It doesn't matter if they're polar or non-polar ions. Doesn't matter. It has electrons. You get this instantaneous dipole form. It's very, very weak, though. Nowhere near like a regular dipole. So these are going to be very, small energies compared to ionic energies and whatnot. But if I have another species next to it, and it happens to be moving slow enough and be close enough, remember intermolecular forces are close range. So this other species is moving, and you get this brief flash, and it happens to be close, it may notice that, right? We'll draw that on the next board. It may notice that brief flash, and that can be affected by that. And it could induce a dipole on another species, even if it's non-polar. So you get this instantaneous dipole causing induction, inducing a dipole on a neighboring species. Let's draw that on the next board. While I get this cat hair out of my eyeball. All right, let's watch this process in play. You ready? So start here. Let's just say we've got any species. We'll just assume it's nonpolar. It's easier to see for nonpolar. So you got this symmetric electron cloud distribution, right, in a nonpolar species. You've got electron fluctuations going on, and all of a sudden, flash, an instantaneous dipole forms. It's real brief, real temporary, going back and forth and back and forth and back and forth and back and forth. And if nothing's near it, no big deal. It just flashes back to symmetric, then to asymmetric, then to symmetric. So you get this instantaneous, very weak dipole forming, and then it goes away, right? So it's actually flashing back and forth between those. But now, loop-de-doop-de-doo, somebody comes along and happens to be really close to this particular species. When that flash happens, that instantaneous dipole forms, and this neighboring species happens to be really, really close and moving really, really slow, do you think it's this electron cloud of the new neighboring species? Whether it's the same species or not, as long as it has an electron cloud, right? It's going to notice that little temporary dipole. If it's moving too fast, if it's too warm, it just goes on by. If it's too far away, it doesn't notice it. Just goes on by. It's got to be close. It's got to be moving slow, i.e. colder temperatures, depending on how big they are and how strong these forces are. So what's going to happen, if it's close enough, it's going to sense that little slightly partial negative, which means the electrons aren't going to like it, is it? So induction will occur. You're going to see the electrons shoot over to this side, right, from induction, right? That's induction. And so you get a push of electrons to the other side, where even if this was a nonpolar species, you're going to see that happen. Even if it's polar, you'll see this happen. But if it's polar, it's not as big of an impact. And then you will see these are going to be weakly electrostatically attracted to each other. And this is your London Dispersion Force, or instantaneous dipole induced dipole force. Right? So it induces a dipole on the neighboring species. And if it's moving slow enough and close enough, that can lock into place. And this is how nonpolar species can actually condense into a liquid, right, from a gas, even though they have very, very, very weak intermolecular forces. We'll look at the energetics of this in a second. You wouldn't imagine noble gases being able to liquefy. They're just monatomic, little, just atoms moving around in the gas phase. You wouldn't think there's any attraction between them, but we can liquefy them. It's got to be pretty cold, right? Same with the, methane and the nonpolar halogens, Cl2 and Br2. You wouldn't expect those because they're nonpolar, but there's obviously some force doing it. So thank you to Fritz London for figuring all this out. You got how that works out? Let's take a look at the energetics because they really vary. These are nowhere near as distinct as ion-ion, those kinds of things, because it dramatically is affected by the size of the species. The more electrons there are, the stronger this effect it will be. Let's take a look at some numbers and do some specific examples. All right, you ready for the statement? So hopefully that makes sense. The more electrons there are, right, the bigger the species is, the more electrons it has, and if it has more electrons, it's more polarizable. It has a larger polarizability. Its electron cloud is more easily distorted. See what I'm saying? So in that case, right, the instantaneous dipole would be stronger, and its induction on another species would be stronger as well, right? So the dispersion effect is higher. The more electrons there are, the larger it is, the stronger the dispersion effect, and therefore the stronger the London dispersion forces. Now, since sizes can vary dramatically, remember on the periodic table, right, atom sizes get larger as you go down quite dramatically. You're going to see a pretty broad range of energies for LDF, or London dispersion forces, or instantaneous dipole induced dipole forces, if you want to run around saying that, making people feel awkward, right? You get ranges from really wimpy, right? Remember, hydrogen bonding's upward in the 40 plus range, dipole dispersion somewhere in the 10, 20, 30 range, things like that. Ionic forces, 400 plus kilojoules per mole. There's, it just depends. So these are a lot weaker than most of the other ones, especially the smaller. So you get the really small species, like helium atoms and whatnot, they're going to be pretty weak. We're talking 0.1-ish range kilojoules per mole. But as it starts getting bigger, especially like hydrocarbons, you start to get to octane or decane with 10 hydrogens, or something with 30, 40, 50 carbon atoms in it that's nonpolar, right? These dispersion forces become pretty dramatic, and you can get up 40 kilojoules per mole. You're starting to push hydrogen bonding, right? So you can see really, really large nonpolar molecules can start to have intermolecular force strengths, the LDFs, comparable to the hydrogen bonding strengths for really small molecules like water and stuff. All right, so just because something's more polar doesn't mean it has stronger intermolecular forces than something nonpolar if they have dramatically different sizes. And we're going to relate size to molar mass. It's a good kind of a rough way of looking at it. But if they're equivalent in size or molar mass, then obviously something that's more polar will have stronger intermolecular forces than something nonpolar, right? So we're going to find out everything has a mixture of London dispersion forces, and if it happens to be polar, it could have dipole forces and London dispersion forces, or hydrogen bonding and London dispersion forces, or ion-ion forces and London dispersion forces. Everything automatically has London dispersion forces. They may or may not be significant. Maybe 5% of the total intermolecular forces, or 10 or 50. If it's nonpolar, it'd be 100%, right? So let's take a look at some of the trends with size, and then we'll play around with different molecules and see if we can say which one would be higher or lower, et cetera, et cetera. Ready to look at some trends? Hopefully this will make sense to you, right? So let's look at the halogens. Now we know in their normal states, they're diatomic. So we got the fluorine, chlorine, bromine, iodine. I didn't do the astatine, right? Radioactive. Let's look at atomic size. I actually wrote the numbers down. I wouldn't expect you to memorize that, but you do know that they get bigger as they go down. Okay, so I didn't do the molecular size. These are just size of the atoms. So the diameter of fluorine atom be 71 picometers. Chlorine would be 99, bromine 114, iodine 133. As you go down, that would make sense, right? The atomic radius gets bigger, and stick the two together, and you can see that becomes more dramatic, right? Increasingly getting bigger, which means more. Obviously, there's more electrons. It's got a bigger volume, bigger electron cloud. It's more polarizable. Right on. So the instantaneous dipole effect is going to be stronger, and then the induced dipole effect is going to be stronger, making stronger London dispersion forces. You can relate atomic size to molar mass in most scenarios, right? The trends follow. So if you're looking at, which, non-polar species has the stronger LDF forces, you can just look at the molar mass, and the larger molar mass is typically going to be okay. You don't really have to look at the sizes per se, because you got the periodic table. You can actually calculate molar masses. So if you just take the atomic mass times 2, you get, close around 38. I did atomic mass units there. You could do grams per mole. Chlorine, 70.9 something. Bromine, 159.8-ish, and iodine, it's pushing to almost 254. So it gets dramatically more heavier, right? The larger atomic mass as you go down. So dramatically larger London dispersion forces, which we would think would change the boiling point, right? So we have increasing London dispersion forces, which means that attraction is stronger, so it takes more energy to separate them. So in order to boil the species, to take a liquid and break those, because that's what, vaporization or boiling is breaking the intermolecular forces so those can go off into the gas phase, right? So negative 188 degrees Celsius for fluorine. For chlorine, about negative 35 degrees Celsius. For bromine, pops above 0. Now it's pushing, 58.8, almost 59 degrees Celsius. And then iodine pushes 184. So pretty dramatic increase in the boiling points, because you're seeing a pretty dramatic increase in the London dispersion forces. It takes more energy to break those, more thermal energy. Now what I want you to do is, you probably know this from periodic tables, we could predict the state at room temperature, right? These are effects of intermolecular forces. Let's take a look here. Room temperature, depending where you're at, maybe if you're, in a blizzard right now, it might be pretty cold inside, right? Inside the room, not outside freezing your butt off. I'm from Minnesota. I know what negative something, it's not negative 40 degrees Celsius wind chill. I'm going to die, right? Well, Fahrenheit. Right, which isn't negative 40 degrees Fahrenheit the same as negative 40 degrees Celsius? Isn't that the one that's the same? That's the one point where they switch over. Check that and let me know. But it was really cold. So inside a room, say you're inside your lab room or something. Now, I'm in Southern California right now, so we're probably talking 22, 23 on some warm days, up to 25 degrees Celsius, right? Getting pretty hot. But it may shoot down to 17, 16 degrees Celsius if you're in a colder area. So let's just take, around 20 degrees Celsius as a typical room temperature. Well, if it boils at negative 188 degrees Celsius, I think that would be a gas at room temperature. The thermal energy at room temperature is enough to break those London dispersion forces. And so you'll see fluorine as a gas. And if you ever are around a fluorine gas leak, run! Okay. Chlorine, most of you realize that if you see it, it's a green gas at room temperature, because its boiling point is negative 35 degrees Celsius. That's below room temperature. So the thermal energy at room temperature breaks those intermolecular forces, and chlorine happens to be a toxic green gas from a green dragon. Okay, anyway, bromine, different scenario. 58.8 degrees Celsius is above room temperature. See that? So the thermal energy is not enough to break the London dispersion forces, right? To put that in the gas phase. So bromine happens to be a liquid, right? Bromine and mercury, I think, are the only two liquids at typical room temperatures. There's some that are pretty close, that like melt in your hand, which is a lot of fun. Now, iodine, dramatically higher boiling point. Now, I didn't do melting points and stuff on here, but that's so big. And you may know iodine, right? It's these cool little dark, kind of purplish black crystals that sublime into a purple vapor, which is pretty neat. But hopefully you can understand why those states are, which you probably already knew this. But now you can explain why based on the boiling point. Now, I'm not going to make you solve for boiling points in my class, but I would expect you to be able to compare. I could say, hey, rank these from lowest to highest boiling point. But you don't have to tell me what the boiling point is, but you could be able to rank them. See what I'm saying? And we could put, this same trend would be for enthalpies of vaporization, the energy it takes to vaporize 1 mole of that particular liquid, right? We got it? We good? There's another effect we have to look at, because remember, intermolecular forces are based how close you can get to them, right? So it's not necessarily just molar mass. That works for most scenarios. But you also have to we're looking at the size. So when you get to organic molecules, you can get to some weird scenarios where you may have 2 different species with the same molecular formula, but they're connected differently. They call them isomers, right? So, C4H10, I could probably draw several, good Lewis structures for that. But you get these molecules that some are kind of straight and some are branched or curvy in some scenarios. They can't approach each other the same way. And so that the polarizability of some are more than others. So let's take a look at the impact of molecular shape. Not going to be too important for general chemistry, but it will be for organic chemistry or biochemistry later on down the road. So let's look at the effect of molecular shape on London dispersion forces above and beyond the molar mass. All right, so let's take a look at this impact. Again, more important for organic chemistry. Molecular shape effect on LDF. This is above and beyond the a molar mass of something. So if you can get what are called isomers, 2 different ways to draw a Lewis structure for the same molecular formula. If you have straighter or more elongated molecules versus, I spelled it wrong, branched. Branched. Whiteboard spell check. Right? If you have more branched molecules, right? So straighter and elongated versus more, compact, branched, something like that. The straighter ones are more polarizable than the branched ones, and I'll show you some pictures of them. And they can stack. They can get closer together. It's like stacking pencils, right? They get closer together, so they have stronger intermolecular forces. They can approach closer. So even though they have identical molar masses, you wouldn't think they would have different boiling points or LDF forces. They do. For example, if we take butane, or I say butane, right? Butane, C4H10, I could draw it as just a string of 4 carbons in a row. Or I could do 3 carbons in a row with a CH3 branch coming off. Still C4H10. These are isomers, right? Same molecular formula, different structural formulas. But do you see how this is more elongated? It's straighter. They call it a straight chain. The carbons are in a straight chain, where this one has a branch coming off. So I'm going to show you some models on how these stack differently. But this one is going to have stronger London dispersion forces than the branched one. So we would expect this one, even though exactly the same molar mass, this would have a higher boiling point than the branched one, and you can go measure those, right? So let's take a look at the straight chain. So this is C4H10, right? The blacks are the carbons, the whites are the hydrogens, and you see, you've got the tetrahedrons and stuff going across. But if I bring a second one, woohoo, right? They're both straight chain. Do you see how they can get really close to each other? Fits in perfectly, like puzzle pieces. So I can just stack one after the other. They can get really, really close, distort the electron clouds of each other, and you can get the instantaneous dipole forming for this one, causing an induced, if it's cold enough, right, and close enough, and they can get really close. So these intermolecular forces lock on easier, and you get the instantaneous dipole inducing a dipole on the neighboring one, and they lock into place. And then another one comes in, and that LDF, and so you get these layers of them, and boom, it can liquefy out, C4H10, right? Let me pause it. I'll make models for the branched one and show you how it's harder to stack those. Hold on a second. This takes a while. All right, so here is the one with the 3 carbons across, all right? Plus the CH3, what they call a methyl group, by the way. CH3 group coming off, so it looks like this. So you see how that's more compact. It's not as a straight chain. It's not straight chain. It's not elongated. So when they're coming in, you can't get the entire electron cloud. There's less electron cloud exposure, if you think. So when they come together, right, they can't get as, remember how nice and snug and tight the straight chain one was? But now you've got these branches that get in the way, right? There's terms for that in organic chemistry. So I'm having issues here. So they can't quite get as close, And so the instantaneous dipole on this one doesn't create quite as strong as an induced dipole on this one. It's not as polarizable. So the London dispersion force is weaker and it would have a lower boiling point. Fitting, right? So again, not as big of an effect that we're going to see for my class, but it may pop up every once in a while. But for general chemistry, traditionally, you could just look at the molar mass and say bigger molar mass, right? It's proportional to more electrons, proportional to a bigger molecule. And if it's nonpolar, it's going to have a higher London dispersion force effect. But what I want to do is end this video real quick when we're comparing species that are not just nonpolar. So this works great for just nonpolar species. Just compare the molar masses. Bigger one wins, stronger London dispersion forces. But what if you've got polar species or ions and stuff? They also have electrons and London dispersion force effects. So you have to compare and go, oh my, how much of the intermolecular force strength is due to the London dispersion force effect versus the polarity effect? Oh, it gets a little more complicated. I tried to eliminate that competing factor on exams, but let's talk about it. All right, it gets a little weird when you break it down, and I won't ask you to do this on exams or tests. I try to take away the contrast between the factors of size, right, and the London dispersion force, and then polarity as well, because they can be counteracting a little bit from what you would imagine. Let's take a look. Would you agree nonpolar species only have London dispersion forces? That's it. They can't have hydrogen bonding because they're not polar, right? But polar and ionic species could have hydrogen bonding, dipole-dipole forces, ion-ion forces, but they have electrons, so therefore they also have London dispersion forces, right? So if I give you a polar species, for example, water, and say what intermolecular forces does it have, or what van der Waals forces does it have, you say, boom, immediately London dispersion forces, because it has electrons, not a lot because it's tiny, and it can hydrogen bond, boop. Right? So it'll have two. But if I say argon, you say, LDF only, nonpolar. But if you break it down, which I won't ask you to do, let's take a look at HCl. We know if you do the delta En, that's a pretty highly polar molecule. Molar mass, a little over 36 atomic mass units or grams per mole. And if you do, if you take computational chemistry, you can actually calculate these using software programs, not in your head. It's about 81% London dispersion forces and about 19% dipole-dipole forces, right? It's a combination of the two. Obviously, the London dispersion forces appears to have a much larger effect. Boiling point's around 188 Kelvin. I won't ask you to predict those either. But I could have you trend things. Well, let's look at HBr. So bromine has a lower electronegativity than chlorine, so it's less polar. It's still polar. The delta En is not zero, right? But it is still polar, but it's less polar than HCl. So it has a larger London dispersion force effect. Plus, it's a lot bigger, right? It's about 80, almost 81 atomic mass units. So it's a bigger species. So it has stronger London dispersion forces than HCl. And it's also less polar. So it's about 94%, give or take, London dispersion forces, and about 6% dipole-dipole. So the van der Waals forces is a little less impacted by the dipole-dipole. But the boiling point is 206, right? So it's less polar than HCl. So you'd think HCl would have a higher boiling point because it's more polar, right? But it's a lot smaller, right? HBr has over double that. Bromine atom's huge compared to the chlorine, so it's more polarizable. So much stronger London dispersion effect. So you can see if you've got species that are both polar, but one's a lot larger than the other one, the London dispersion forces really click in. Right, so it has a higher boiling point, not that much higher, but it's higher because it's a lot bigger, even though it's less polar. You see the contrast there? So on my exams and quizzes, I will try to give you maybe two polar species that are pretty equivalent in molar mass. So you would say they'd have roughly the same London dispersion force strengths, and the difference would be the more polar one would have the higher boiling point, right? So I try to take out the London dispersion force effect. Or I could give you two species of dramatically different molar masses and maybe different polarities. And the one that's a lot larger would have the much stronger LDF and probably would have the higher boiling point, right? But typically what I'll do is I'll give you like a string of 3 non-polar species. So you don't have to worry about polarity at all. You can just do the molar mass or size effect with just London dispersion forces. Or I'll give you 3 polar species of about the same molar mass, so you can just look at the polarities. Right, so I try to get that conflict out of the way. You'd be on a test going, I don't know, man, this one's bigger, but it's less polar. What do I do? Now, bromine, of course, diatomic bromine, that's nonpolar. Delta En is 0. So it's 100% LDF. There's no dipole-dipole forces, nothing in there. But it's way bigger. You know, you're pushing 160 atomic mass units or grams per mole. So the boiling point's upwards of 332 Kelvin. So even though it doesn't have any dipole-dipole forces, its London dispersion forces, its polarizability is so much greater. The London dispersion forces are so much greater. It has a higher boiling point than even those polar species. See the contrast there? Oh my goodness. So let me give you a type of question I might throw you on an exam. All right, the first kind of question I will ask you on quizzes or exams. I'll give you 2 species and have you compare them, or more. I could give you 2 or more. So for example, say diatomic oxygen versus nitrogen monoxide. Which one would have the higher boiling point, or which one would have the stronger London dispersion forces, yada, yada, yada. So you'd look at oxygen and go, well, it's obviously nonpolar, right? Whereas NO is polar, right? The delta En is not 0. Molar masses are almost the same. That's within 4 or 5 atomic mass units. I'd consider those pretty much the same, right? So since they're roughly the same molar mass, they're going to have roughly equivalent London dispersion force strength. Even though O2 only has London dispersion forces, NO has London dispersion forces and dipole-dipole forces, right? And I won't ask you the percentage breakdown of those. So oxygen, I won't ask you what the boiling points are, but oxygen boils about 90 Kelvin, give or take. NO about 121. So NO is quite a bit bigger, even though it's about the same, even though it's lighter actually, but they're roughly the same because of the dipole-dipole forces. So when you're comparing species with about the same molar mass, the one that's more polar is probably going to have the bigger boiling point, stronger London dispersion forces. Cool with that, right? Especially if it had hydrogen bonding or if it was an ion or something. The ions totally dominate, almost regardless of the mass, right? So now let's look at the other one where I give you maybe they're all nonpolar or all have roughly the same polarity. Then you look at the molar mass. All right, let's play around with the last type of question, right? So in this case, they're going to have similar polarities, but differing molar masses, right? The other one, they had similar molar masses, differing polarities. So let's take a look, and I could give you a string of nonpolar species, polar species, as long as they all had dipole-dipole forces, or all had hydrogen bonding, or all had just London dispersion forces. Now for ionic species, you could use Coulomb's law. That's a little bit different. So let's take methanol, right, an alcohol with 1 carbon, ethanol, an alcohol with 2 carbons, or butanol, in this case 1 butanol, where the OH is on the first one, straight change butanol. So we got these 3 alcohols. You see the OH group on all 3? So all 3 have hydrogen bonding, and all 3 have London dispersion forces, because they have electrons, right? So since they all have hydrogen bonding ability, we're going to ixnay that out as a comparison between who has the strongest London dispersion forces. Now we took out that factor, we have to look at the size. Obviously they get bigger going down. So CH3OH is the smallest and the butanol is the largest. You don't even have to calculate molar masses to do that one. You just got more carbon atoms, right? So it's getting bigger. So as it gets bigger going down, the larger molecules, the butanol has a larger electron cloud. It's more polarizable, stronger instantaneous dipole, stronger induced dipole. So it has stronger London dispersion forces, right, as it gets bigger. So let's take a look at the trend of the boiling point. So methanol is about 64.7 degrees Celsius. Ethanol, both have, so it's pretty high because of the hydrogen bonding. For such a small molecule, that's a really high boiling point. Yay, hydrogen bonding. But ethanol also has hydrogen bonding, but it's bigger, right? So you'd expect a slightly higher boiling point, 78.4 degrees Celsius, right? And then we jump up a couple more carbons to butanol, also has hydrogen bonding, but it has way more carbons. It's a lot bigger, and that jumps up to 117.7. So that follows the trend of the increasing London dispersion forces with equivalent polarities. Now, one thing we're going to look at a little bit later is solubility in water. So that like dissolves like. You see the OH? Right? If I cover that up, water thinks that's water, right? So they can both hydrogen bond, so they have similar intermolecular forces. So you'd consider methanol to be very soluble in water. Same with ethanol and stuff. But as you add more carbons, it becomes more nonpolar. See that? So the solubility would decrease as you add more of a carbon chain as it's getting through, because the London dispersion forces has a bigger effect. It becomes more nonpolar, to the point where if you add enough carbons over there, it would become insoluble in water. And you can actually get molecules that are so big and you might have an OH group on one end and all these carbons on the other, where it's so big, it could be soluble in both a polar solvent like water and a non-polar solvent like benzene or something like that. That's kind of cool, right? Those big ones can go be soluble in both. Kind of weird. But anyway, that's just a little intro into when we get into solutions later on down the road. So hopefully this is enough for you to be able to compare and contrast molecules and be good with these crazy London dispersion forces. You guys are awesome. So what we're going to do in the next video is look at the impact. Now that we can tell two different species, whether they have stronger or weaker van der Waals forces or intermolecular forces, and what type they have, we could actually look at liquid properties. Say which one, like I said, we've already looked at, has the higher boiling point. For solids, melting points. We're going to look at things like surface tension and viscosity, and we're going to look at the ability to vaporize, those kinds of things. Let's do it. Application, application, application.